Hi, welcome to Straight A Programming. Today I'm going to talk about binary search trees. So a binary search tree is a nonlinear data structure, and you have a root, that's the first number, and you have left, you have the less number, and it's called the child, and then the right you have the bigger child. So these are siblings. 5 and 15 are like sibling nodes. And these are all nodes, and the values are on the nodes. It's they use nodes like a linked list. And so down here, the ones without the the parents, and these are parent nodes. Parents with the children are those are child nodes, and child nodes without children, or nodes without children, are leaves, are called leaves. And so you can do certain functions with the binary search trees, like search, like a binary search, which has log in, because you could quickly compare the value you're searching for, and quickly just cut half the tree out, because it's either going to go to the left or to the right, and each subtree is going to be lower than the parent. So so to implement a binary search tree, I created a stack uh, using the linked list. Linked list I talked about, a singly linked list I talked about in a previous tutorial. Um, so the stack, I use that linked list and to implement a stack. And a stack is like last in, last out, meaning you just stack some papers, and the only paper that, and you can pop the stack, like right here, and popping the stack is it's like you're stacking papers, and you're and when you pop it, you just the last paper that was put in the stack you can access. Um, so last in so last thing in, and a queue is like a line, like you're waiting in a line at a store or something. First in, first out. So you enter in queues, like you put data or the node in the back, and you'll get it from the front when you DQ it. So so there are different functions in the queue, and I use it to implement some of the functions for the binary tree. And the binary tree is like the linked list, where I create a node. So I parameterize the type T. I use a generic, and I did not use the generic in the linked list, which ended up causing warnings in the VS Code. So I would have to change the linked list, but since I'm using all integers, there are not going to be any typecasting errors. I'm just using integers anyways. Um, so um, so there's a public values, a generic type, and then I create some variables in the node that the left points to the left child, the right child, and then for later on I use a parent. You need this node, the parent. Use the parent node for a binary search tree that rotates itself. I'll talk about that in another tutorial. It's called AVL. But this is just going to be binary search tree. So this is the constructor. You initialize the t values, left, right. Um, there's the public, and then I create the binary search tree class. And so I create the private, the root, the first node, and this is the constructor to create an empty tree. And this is a constructor to build the tree. it out, and but I also have another. Um, I have a class to print it out a little bit better, like you saw in this, in the other. So I can print it out better, like that down here. Um, so this prints it out just like an array type of thing, a string. So a get root, set root. Now, I'm not going to use that in today's tutorial. So add a new node with a value to the tree, and then there's just the helper method. Normally you'll see this in a recursive way. I did this iteratively. So this is just if the root is null, meaning that tree's empty, just the new node is going to be the root, and so you have the node current pointing to the root, and that's how you start. And the parent equals null, and then when current is not null, it'll add the node in the correct place. If it's left, it's going to be in the left subtree. If it's right, it's going to be in the right subtree. And like I said, normally this is recursive. So it just keeps going to the left or to the right and places the node in the correct place. The parent node is points to the correct position. You place the new node in the correct child position. And then for it's either going to be left or right depending on if it's bigger than the parent node or less than the parent node. And then you just return the root of the tree. And this is remove. And so it returns a true or false depending on if something removed. So a value is going to be entered into this as a parameter, and that's what you search for. And this one removes all those values. So you just traverse, put the current equals root and parent equals null, and then you traverse the tree and you compare each one. And so if the node is not found, it returns false. Now to remove, um, you have to fix the tree. When you remove the node, so say you remove 15, you remove the node, um, if you remove 15, you have two child nodes and a parent node. Something needs to be done to restructure this tree. So you would put 18 there and keep 12 as a left child of 18 if you remove 15. If you remove a leaf node, you just remove it, and there's no longer you set the child, the five nodes child to right child to null. So and that's all you got to do in the binary search tree. The AVL balances it out. It'll balance out the whole tree. I'll talk about that a little bit more about what the definition of a balanced tree is. It's basically the height balance. The height's got to be within a certain distance. So if it's a leaf node, you just put um, you just set it to null. We set the root to null or the child to null. If it's the root node, if there's only one child, you just replace the node that's going to be removed with the child, or it replace the root to the child node. And like I was talking about case 3 first there, if it's like a node in the middle with a parent and two children, um, they refer to it as replacing it with the in order successor. This is the leftmost or smallest child of the right subtree. So 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 we create some node variables for case 3, current and current dot write. Set the successor so use the current successor value is equal to successor value, and you remove the successor node. So if the successor is left child of its parent, update the parent's left child to the successor's right child. Successor is the right child of its parent. Update the parent's right child to successor's right child. And then return true. And find min, you just traverse the array on the left side until a node dot left is null. Basically until you reach the lower left leaf, and then return that node. And find max is you just traverse the tree to the right subtrees, go to all as far right as possible in the subtrees, and until it's null. And that node dot right is null, and just like up here, node dot left is null. It means the leaf node, and so just return the node. And now in order transversal is performing an order transversal of a tree and returns a queue of the visited node. So this is where I use the stack abstract data structure and the queue data abstract data structure. Um, so it returns a queue, and I already created those classes. I created a new queue instance to hold the nodes, and so I'll call the helper function with the root the queue, and now here's the in order function. And I use a stack. So I create the root here. So I'll traverse the tree and reach the leftmost node of the current node, push the left child of the current node onto the stack.push, and go current.left. And so then I'll start popping, and then I can queue what I pop on top of the stack. And then I start visiting the right subtree. And so I'm going to give an example for this tree. Current is set to the root node 10. Stack is empty and the queue is empty at the start. So I created instances. The first iteration, I push nodes 10, 5, and 3 onto the stack. So remember 10, 5, and 3. So 3 is going to be on the top of the stack. Right there. Current is now null. Pop 3 in and queue it. 3 right here. So 10 and 5, what's left in the stack, so now current is now null. 3 has no right child. In the second iteration, while current is null, we skip this loop. In the outer while loop, pop node 5 from the stack and then queue the value. So now we have 3, 5, and you can see what's starting to happen. Current is now 7. Right here, current is now 7, which is the right child of 5. Third iteration, the inner while loop push node 7 onto the stack. 10 and 7. Current is now null. I pop 7 from the stack and then queue its value. So 357 is in the queue now. Current is now null because 7 has no right child. In the fourth iteration, the inner while loop current is null, so we skip the loop. In the outer while loop, we pop node 10 from the stack and then queue the value. So 357, 10. Current now 15, right child of 10. See it there? Fifth iteration. Inner while loop, push node 15 and 12 onto the stack as we move to the leftmost node. See that? 15 and 12. So the stack has 15 and 12. Current is now null because 12 has no child. Pop node 12 from the stack and then queue it. And now the stack just has 15, and there's the queue. You can see it. 12 has no right child. Current is now null. 6th iteration. Inner while loop and current is null, so we skip this loop. Pop node 15 from the stack and then queue its value. Current is now 18, which is the right child of 15, which is the max. So now 18 is on the stack. Current is now null. Pop it in Q18, and there you got the Q, and that's what's going to be returned with that tree above. So that's the final result. So that's how the in order transversal, so it's ascending. So that's how that works. That's what how that algorithm works. So in main, so I made a few functions. So to add a node, so let's go to main. Oh, there it is. So I created an array. Excuse me, I created a binary tree. So I print the tree out, and then I'm adding add a value 6. And there's you can see from the where added it's compares this is going to go to the left subtree since it's less, and since it's bigger than this node, it's going to go to the right. And then you compare it to this node, and it's its left child. And so there it is. And now that's the add. So here's remove right here, value. So here's the initial values for remove. So 30 is removed. So this is before, there's 30. So when you remove this, you can see 40 becomes the new node, and its left child was 30's left child. So you can see what happens there. And now remove 70 and does the same thing. Now 80 becomes the parent, the node, in replace of that. So that 80 was the in order successor, and 40 was the in order successor of 30. Now find min. Found min of the previous tree, and that was just 20, and the max I found it was 80. And there's the in order traversal. So it's ascending of the same what I was using to find the max and min. The right here, this one. So I just basically put that in ascending order is what in order traversal ends up doing. That's the order it visits the node, basically. But when you print out the value, it ends up being ascending. Because of the way the binary search tree is structured. Okay, so that's basically how the binary search tree works. There's other functions you can write. In the next tutorial, I'm going to be talking about the AVL, which is a self-balancing binary search tree, which uses this binary search tree. But like I said, there's other functions you can write for this. You can search, like, try to find a value. You can count the number of multiple values when you have double values. You got to set a rule for the binary tree if there's multiple values, which child is going to be. Um, There's different types of traversals also. So thank you very much.